Okay, welcome back to another video lecture for Math 1316, Trigonometry. And in this video lecture, we will be covering section 4.4. Section 4.4, if we take a look at the Pearson provided notes yet again, we see that they're really just kind of talking about the graphs for secant and cosecant. So at this point, we've spent an awful lot of time with acute angles and therefore the unit circle values. That's like 30 degrees or like pi over 6, pi over 3, 60 degree, 120, 45, that kind of stuff. And so we're pretty familiar with the values of secant for these particular um, types of arguments because we know that at 0 degrees the cosine is 1, and since secant is just a reciprocal of cosine, we know that if you take the reciprocal of 1, well then you just get 1. At pi over 4, we have the square root of 2 over 2, and at this point we've seen how we can take the reciprocal of a number in that format and it will just be the square root of 2. So really the features that we need to discuss about secant and cosecant, because they operate much the same way that sine and cosine do, because they're based off of sine and cosine, we need to talk specifically about the domain and the range of these functions, because if you were to take a look at the graph, you will notice that it is different in a couple of key ways from the graph of sine and cosine. So the first thing I wanted to do was show you a cosine graph and kind of how we produce the secant graph. So cosine graph is this, I'm going to try to make this a different color here if at all possible. Let me see if I can just do it this way. Okay, I like that one. I don't like them to be red. So the cosine graph is this blue line here. And notice that because secant is the reciprocal of cosine, it is valid for every single possible number along the cosine curve, except for the spots where the cosine is equal to 0. Because if you recall from an earlier lesson, when we take the reciprocal of a 0, we get undefined. That's like writing 0 over 1, so flipping it over is 1 over 0, which from college algebra we know to be undefined. So the domain for secant is all the values of x except for the numbers that correspond to the places where the cosine graph is equal to 0. And you notice that the places where the cosine graph, this blue line, crosses the x-axis, in other words, it's equal to 0, are at like negative 3 pi over 2, pi over 2, negative pi over 2, 3 pi over 2, 5 pi over 2, and so on. And we're kind of familiar with the way that this works before, because it's similar to the asymptotes for a tangent or cotangent graph. So secant has asymptotes at any value, any multiple of pi over 2, where it is an odd multiple of pi over 2. So x cannot equal to any number that is in the form shown here. Okay, so the other thing we should notice is because of this asymptotic behavior, the secant curve goes flying off very, very rapidly. Now we've known since a pretty early lesson that the secant curve has a domain, or sorry, has a range which can be any number larger than an absolute value of 1. And it can also be 1, but it cannot be any number that is in between -1 and +1. So basically, it cannot have the value equal to anything within the range for sine or cosine. It has to be all the numbers that are not in the range except for 1 and -1 of sine and cosine. So the way that we produce this graph, a really nice way to think about it, if you notice all of the peaks of the cosine wave match up perfectly with one of the peaks for the secant graph. And effectively what we've done is we've fixed those peaks in place, and then we've taken the graph and exploded it outwards so that we get these U shapes on the top and the bottom. So let me turn this cosine graph off so we can see what A, B, and C do in this case. Now, if you remember, A controls the amplitude of the cosine wave that secant is based off of. So if I were to set this cosine wave equal to 2 cosine, then I should have an amplitude of 2. In other words, the peaks now happen at 2. And that will match up perfectly to what we know to be true of the secant graph when A is equal to 2. If the cosine wave produces the secant wave by this kind of funny, like graph, I guess, explosion, then if the cosine wave goes up to 2, that means the place where the secant wave has to begin is at 2. And you notice that all that the amplitude does in this case is it excludes a wider range of numbers. So I can no longer have values of secant, this red series of lines, that are in between -2 and +2 when A is equal to 2. When I set it to 3, I can no longer have numbers between -3 and +3. I can no longer have numbers between -4 and +4. So it's just like what the amplitude did for sine and cosine. The only difference is it controls how far apart these upper U shapes and these lower U shapes are. So much like sine and cosine, if I zoom in over here on like the positive side of the graph, you notice that we see the first part of this U shape beginning at 0. Then we see a full U shape down here at the bottom. And then we see this second part of a U shape totaling to 2 total U shapes, one on top and one on bottom, within 2 pi worth of distance, which is right here. At 2 pi, we have one period of the secant function, just like we had with cosine. So that's an important property. The way that we determine the period of a secant or cosecant function is we just use the same calculation that we were going to use for the sine or cosine function. That is 2 pi divided by whatever capital B happens to be. So you can see that in this case, when B is equal to 1, the period is just 6.28, which is 2 pi. And so similarly, remember what the B value controls is how many full periods I'm going to see within 2 pi worth of distance. So when I set this equal to 2, I now see the first part of a U, a bottom U, a full upper U, another bottom U, and then the second part of an upper U. So that's 2 U shapes on top and 2 U shapes on bottom. 2 periods within 2 pi worth of distance. If I set it to 3, you can now count 3 periods, 4 periods, 5 periods, and so on. It gets harder to count after a while. Okay, so effectively what we've established here is that although amplitude has a different meaning with secant and cosecant, it behaves much the same way that it behaved when we had sine and cosine. B still controls the period, how many we see within 2 pi, and so it's safe to conjecture that C controls the phase shift the same way it did before. So remember, we have to be careful with phase shift when it's not given to us in this factorized form, the way that I have it written right here. But C does in fact control the phase shift. It's the left and right movement of this curve along the graph. And the step here is pi over 4 on this slider. So if I wanted to move it pi over 2 to the right, then that would correspond to x minus pi over 2, and we get a graph that looks like this. Now D is very, very boring. As previously stated, D controls how far the midline moves up. And notice that the midline of secant is the x-axis the same way that it is the midline of the cosine graph. So the midline of this blue line is x equal to 0, and also it is the average of the bottommost position of the upper U's and the topmost position of the lower U's. So the midline for secant is also controlled by D. You see when I move it up, it goes up. When I move it down, it goes down. And that is how the secant graph behaves. Now you might have guessed if the secant is just like an exploded version of the cosine graph, then the cosecant will be like an exploded version of the sine graph. So I've changed it. This blue line is now a sine graph. This red line is now a cosecant graph. And A, B, C, and D behave the exact same way. Moving A spreads the distance between the U's apart, right, making it negative, flips it over. B controls how many periods in a 2 pi worth of distance that we see. C controls the phase shift from right to left, where positive values of C result in x minus a number and therefore move the graph to the right, and negative values of C result in x plus a number and therefore move the graph to the left. D again moves the midline up and down. Okay, now the difference between the domain for secant and the domain for cosecant, just very quickly, notice the range is identical, just like the range for sine and cosine is identical. Even the periods are identical, 2 pi divided by b, but the domain for cosecant is a little bit different because now instead of being based upon the places where cosine is equal to 0, we're based upon the places where sine is equal to 0. And sine is equal to 0 at every multiple of 180 degrees, 180 degrees, 360 degrees, and so on. An easier way to say this is that x cannot be any number in this form, n times pi, where n is an integer. So it cannot be 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, because that's where the asymptotes occur. Also, examining this graph here, if I were to put a vertical line at x equal to pi, you see we have an asymptote. If I change it to 2 pi, it's another asymptote. If I zoom out on this thing a little bit and I do it 3 pi, you see this is where all of the asymptotes are. Any integer multiple of pi is where the asymptotes are. Okay, so checking back through real quick, let's just make sure we didn't miss anything. A lot of the examples here are about curve sketching. Remember, you want your calculator to be in either radian or degree mode based on the nature of the argument that you're taking. The default way to do this on a TI calculator is to put it into radian mode so that we can see it within a reasonable amount of distance. And so if you use the zoom trig function on your calculator, it will set it so that we can see this graph very, very nicely. That's what they have done here in this little printout on the notes. And also recall that you do not have a secant or cosecant button on your calculator, so you have to enter those as like 1 over sine or cosine. So if I want to type the same thing here, the same exact thing as that top equation, then what I would need to write is y equal to a times, and then I'll make myself a little fraction bar here, 1 over the sine for the cosecant graph, bx minus c, and then on the outside plus d. And this is the way that we would need to type this into the calculator. And you see very well that this purple line overlaps with the red line. They're the same thing if I flash them back and forth real quick. And so that's the way that we have to enter this in the calculator. If you wanted to do a secant graph, then of course you do the same thing down here, just changing it to cosine. So the red is a secant graph, changing that to cosine, you see that the purple line still overlaps it perfectly. So this is the format we'll see on the tests and from Pearson and from the books, and this is what we have to type in to our calculator. I neglected to mention this in the previous video because we were talking about cotangent, but if you want to draw a cotangent graph, it's basically the same thing. You'll have a times 1 over, and then you'll have the tangent on bottom, and then whatever this stuff, this bx minus c business is on the bottom as well, plus d on the end. That's the way you would enter this in the calculator. Okay, so if you understand those things, then you understand section 4.4.